So in this warm-up, you guys are asked to create a tree diagram. So they're working on it now, and you guys are going to start by separating them into classes, and then based off of the classes, their decision as to whether they're planning to go to college or not. That would be my suggestion. So that is what my tree diagram looks like. It doesn't really matter where the words and numbers show up as long as you can interpret it on your own. But you'll notice when you're branching off of like seniors and you say yes, whether they're planning to go to college or not, they didn't give you both of those numbers because they're complements of each other. So the 0.71, you can find the 0.29 by just subtracting that off of 100. Okay, so the next question I'm going to ask you to fill out is somewhere. What is the probability that they plan to attend college? So you have to look at separate branches here for everybody who plans to attend college. So you got to talk about the seniors and the juniors and the sophomores and the freshmen. And your math kind of looks like this. So you'd take the 0.29 times the 0.71, and you'd add that to 0.26 times the 0.76. And then the 0.23 times the 0.81. Add that all up, 0.22 times 0.84. And I believe you get 0.7746, but I would love someone to confirm that math. Is Paige checking it for me? Oh, good. So this is kind of how your FRQ on Wednesday is going to develop as well. You're going to have to make a tree diagram. It's good. Okay. You're going to have to make a tree diagram, answer one of these like overall combined probability questions, which is really an OR question at its heart. It's the probability that you're a senior who will go to college, or a probability that you're a junior who will go to college, or the probability that you're a sophomore, and so on and so on. Any questions on that one? Because honestly, if you can't get this part of the FRQ right, you're probably going to struggle on the next part because we're going to use this answer. Yes?
So that's literally what you have to do. There's literally nothing else writing.
Not for that first question. Nope. What you might want to do is put in some probability notation. What would that probability notation look like? Probability of?
Total. Yes.
Plan to attend college? Yeah, and that's what I would have written down too. I would have said probability, P, parenthesis, plans to attend college. I just used words. I didn't define anything as event A or anything like that today. So the second question, I believe, asks for the probability. Does it say given that they're a senior? Is that how it starts off? Okay. Oh, okay. They're a senior. Okay. So the notation would look something like that. The probability that they are a senior given that they plan to attend college. So for me, there's a couple of different ways you can get this probability, but we're really hoping you use your formula for given right off of your formula sheet. So your formula sheet for given conditional probability says you first find the probability of the intersection of those two things. So you find the probability that you're a senior and you plan to attend college. And then you divide it by the conditions probability. So the probability that you plan to attend college. Well, good news, guys. You already found this denominator. You found it in part A, the first part. So the senior and plans to attend college, those would be the senior branch of yes. So what we need to do for that probability is just multiply the 0.29 and the 0.71 together. And that's your numerator. And then divide it by the overall probability of planning to attend college, which you just found. And that's typically how an FRQ in this style will look. They'll have you find something, and then they want you to use that on the next part of the problem. Now, fun fact, if you screw up part A and you still use it correctly in part B, you will still get full credit for part B. You possibly will get credit for the whole thing if you show your work and you just made some epic silly thing like inverted numbers. Well, it's something I would do, so, you know. So then the third part, they ask us for, is it independence? Okay. So it says, figure out if these two events are independent from one another. So plans to attend college and, probability that you're a senior. Oh, by the way, the answer there is 0.2658. Is that what everyone else got or just me? Everyone else got it. Okay, cool. Hey, you're here. So are they independent? There's a couple different ways you guys can show independence, but my favorite one is to take a conditional probability and then just remove the condition. Well, didn't you just find a conditional probability? So I'm just going to do this. I'm going to say, does the probability that a senior given plans to attend college equal the probability of senior?
I got one. Aye.
We're recording, so keep your swearing to a minimum today. Just kidding. There's
I
no
don't give
swearing.
up.
Oh, boy. That was Nico. And he did not swear.
Vote November.
Everyone vote. That's right. 2020. This video is going to be living in infamy forever now.
My political opponent.
Maybe. All right. So, guys, we already found the right-hand side of that. We know that that was 0.2658 from our last calculation. The probability that someone is a senior is pulled straight off of that tree diagram. So 29% senior. Do they match? No. So what you going to tell me? These events are not independent because their probabilities are not the same.
They both equal to one.
That would be very unusual because that would be two certain events. I don't even know what that would look like. That'd be a very boring Venn diagram is what that would look like. Or a tree diagram for that matter. There would only be one branch on it. I don't even know if that's possible, guys. All right, so that's going to be your something like your FRQ tomorrow. You're going to make me a tree diagram. I'm going to ask you an overall like union style probability question. I'm going to ask you a conditional probability, and I'm going to ask about independence. So next, y'all need to find your review, which I believe I gave you.
If we didn't even look at it yet.
No, it's fine. If you haven't looked at it, no harm. I did post the key, and at one point I had a goofy thing on my key, so I reposted it with the less goofy. It was classic Abruzzo, reversing things that didn't need to be reversed. So, at the top here, I think we need to kind of just throw out all the probability rules that we might need to know for this test. And some of them are from your formula sheet and some are not. So let's start with what's on our formula sheet. And you get to use your formula sheet on the test, of course. So there's really only two probability formulas on your formula sheet. The first one being the probability of A union B. What does your probability formula sheet say? Probability of A plus the probability of B, but then you have to subtract any sort of overlap, intersection between them. So it's subtracting the probability of A and B. And you cannot use this on the test, but I think it would be smart for you to kind of notate this for yourself. This union is synonymous with the word or in math. And this intersection is synonymous with the word and. And we learned our lesson on, what day was that? Was that Friday? And we had some interesting probability things to do. Well, when we write out things in probability notation, even if they're words, it really kind of guides to what you're supposed to do next, because these can get really crazy. Now, there's another formula from your formula sheet. That's the conditional probability, and I think the order goes A given B. So the way we find A given B, right off the formula sheet, is the probability of A and B divided by the probability of B. Now, those are reversible. If it was B given A, it would work the same way, except you divide by the probability of A. And like we just saw, you know, sometimes these formulas kind of go hand in hand. Sometimes you have to figure out the A and B separately, and then you can go find conditional later. There's some other problems, other formulas from probability that are not on your formula sheet. I guess they're supposed to be kind of inherent. If I write things like this, though, probability of A and B, and I say, well, what's the formula for that? Well, remember how I told you the reason there aren't more formulas on the formula sheet is because the formulas are all related to each other. So this probability, actually both of these formulas, if you want to think of it that way, both of these formulas are kind of close cousins to rewriting for this guy. So probability of A and B, there's two instances where you have to think about the problem itself. So technically the probability of A and B occurring is the probability of A times the probability of B given A has already occurred. So that is this formula right here kind of rewritten in a sense. But it could just be as simple as the probability of A times the probability of B. And the reason those are both formulas for finding A and B is because it depends on independence, no pun intended there. So if the events are independent from each other, you don't have to worry about B given A given B, because they're independent from one another. Usually these problems show up with some sort of context, and it's a little easier to look at. All right. So I don't think there's any other formulas we have to talk about. We need to talk about like tools in your toolbox though. How do I attack a probability question? Because you've got some things that you know to do. You just have to know, okay, what are my options here? Oh, I already put those on there for you. All right, so example 1 here. If you fail any one of your classes, you're going to get grounded. Okay. The probabilities that you fail a class listed in individual order, so referring to your first, second, third hour, and so on, are that. What's the probability that you will not get grounded? So let's rewrite that in probability notation. Probability that I will not get grounded means what? The complement. Yeah, okay, that's true. We can write it as a complement. Can I also write it as probability that we're going to pass all our classes? And your idea of complement is great because that's how I'm going to figure it out. Now it does say, actually it doesn't say, it should have said, these are all independent from one another. So if you fail first hour, it has nothing to do with whether you fail second hour. Okay. So this question actually could be really easy if you remember the idea of complement. So if I have a 2% chance of failing period 1, what else do you know? I have an 88% chance of passing it. See, that's a glass half full kind of a thinking there, guys. Oh, that's 98. You guys. You're so... I was just seeing if you were paying attention. Yeah. That's what the teachers always say. Okay, let's see if I can get one right this time. So 1% chance of failing, that means I have a 99% chance of passing that one, and so on and so on. I don't have enough colors to keep switching colors, though. So that's another 98% for the third hour. And then 97%. Oh, I'm going to run out of room.
I like these odds.
Yeah, right? You got good odds here. Oops, I'm totally out of room now. Keep going, 95 and 96. Woo! So, I need you to definitely never trust my answer key. Go ahead and crank that in the calculator. Multiply all these together. I got 0.833. I'm really hoping y'all did too. Yeah. This is the first time I've keyed through these in front of children, so you are my guinea pigs. I'm seeing some head nods. That's good news. Good. All right. So that's sort of idea for when I have multiple independent events. I just simply multiply their probabilities together. They have nothing to do with each other, so I didn't have to worry about any sort of conditions. And I definitely didn't need a tree diagram. That would be too much. And this question is really dumb, so I apologize in advance. I was trying to make a question like the one on your test, and I was out of creative energy, so I made a really stupid question. So you've got a proportion of random socks in a drawer. None of them are paired up in pairs because you're a psychopath. And then you have to pull out 2 socks, and for some reason you're going to pull out the first sock and put it back in. Don't question it. Just go with it. Okay? You're replacing it. And then you're going to pull out a second sock, and I want the probability that you actually get a match. I guess. I know, stupid. Really bad question. Okay, so there's 2 events here, right? We got the first event, you're pulling out the first sock, and then you got the second event, you're going to pull out another sock. So here's the problem. What does it look like if you have a match? 2 of the same. So like it could be 2 black socks. What else could it be? 2 stripe, 2 brown, 2 green, 2 white. So I have to figure out all those probabilities and add them together. That's what I have to do. So for instance, pulling out 2 black socks would be 0.2 times 0.2. Are y'all okay if I just write that as 0.2 squared? So took care of black. All right, brown, that would be 0.1 squared. And then took care of that. All right. Green would be 0.1 squared. Took care of that. White would be 0.4 squared. Took care of that. And then stripe. Again, I don't know why you're putting the sock back in, but you are. And the reason we're adding these together is because at its heart is really an or question with a bunch of ands mixed in it. You know, what's the probability that I pull out 2 black socks, or the probability I pull out 2 white socks, or the probability of pulling out 2 brown socks? So crank that in the calculator. And I got 0.26. Seeing a head nod. Were you just trying to affirm my yes? Okay. Sometimes I think you guys are trying to pity me and you just nod your head like, yeah, that's what we got. The internet will tell you you're wrong. I won't publicly post this to YouTube because the world doesn't need to hear this. Failures? Jeez. Okay, so here's another technique that we might want to employ on a problem. Could you make a tree diagram? So for me, I often resort to diagrams because I need that in my life. So a machine works 82% of the time. And then even when the machine does work, there's a 2% chance that no one will show up to work the shift. Yeah, it's a very timely problem, isn't it? When the machine does not work, there's an 80% chance that someone will show up to actually run the shift. Do you feel how this is a tree diagram? Besides me telling you at the top, hey, make a tree diagram. You have 2 kind of decisions that have to be made. Does the machine work at all? And then will the person actually show up to work the shift? So this is a great event for a tree diagram. This will be a multiple choice test, so you don't have to get crazy with your diagrams like labeling things. But technically what we're doing is like any given shift is what we're choosing from. Now, the machine works 82% of the time. So the machine works. So what's the other half of this branch? Yeah, and what does that 18 mean? Okay, the machine does not work. I don't know why I'm writing so silly. Does not work. Okay, now next clue, it says 2% chance that no one shows up to work the shift even when the machine works. So that's your next branch off of the machine working. So, okay, so we got a 2% chance that no one shows up. So I'm going to say no worker. So the complement part of that branch would be 98% that there is a worker. And then they tell us something similar down here. Just make sure you're kind of keeping your notation consistent. So if the machine doesn't work, there's an 80% chance that someone does show up to work. So I'm going to write that down here just to keep it consistent. 80% chance you have a worker, which means we have a 20% chance that there's no worker. So we got a diagram. It's making sense. Now let's read the question. Find the probability that the machine does not work, but someone does show up to the shift. So the machine does not work. Which branch am I looking at? Down here, yep. And then someone does show up to the shift. So this is a conditional probability of sorts, but it's really a combined and probability. So we're multiplying those together. That's how we're getting that answer. I believe you. 0.4, okay. So I like to write them as decimals only. But if you want to write 14.4%, I love it. Now this next question says, find the probability that no one shows up for the shift. So there's 2 places on this tree diagram where nobody shows up to work. It would be, assuming the machine works, you get no worker, but also what happens when the machine doesn't work. And what you're going to do is you're going to find both those probabilities and you're going to add them together. Get 0.0524? Maybe. So on any given day for the shift, there's about a 5% chance that your worker won't even show up, regardless of what's happening with your machine. That's not a good work ethic at all, is it? It's very timely, though, isn't it? Chick-fil-A's got to shut off one of its drive-up window areas because there's not enough workers at Chick-fil-A anymore. I know it's sad. All right, so that's a tree diagram. That's how it could usually answer some questions, help you answer some questions. Now let's look at a Venn diagram, my favorite. I'm going to warn you, this question's really hard for kids because you got to read into it a little bit. But it's very similar to the one on your test, so pay attention. At our school, 35% of the students are classified as a freshman. 29% are classified as athletes. But can you understand there's some sort of intersection between those two? There's got to be some freshman athletes in there, and we're going to keep reading to figure that out. Of the freshmen, 20% of them are athletes. So we have a pretty boring Venn diagram that just talks about freshmen and athletes. We're not considering the other classes. And it says 35% are freshmen. So I'm going to write that not in the circle, but up here. Now I'm going to go ahead and write it as a decimal as 0.35. But what some kids like to do on Venn diagrams, they don't like percentages in their Venn diagram. They would rather just have numbers. So if the decimals are bothering you, just pretend you have 100 students in your school. And that way all these percentages could just be called integers. So like 35% would be 35 and so on and so on. So what percent are athletes? That's 29%. This is the part kids like don't handle well. Of the freshmen, 20% are athletes. So a lot of kids want to put like a 20 right here.
Would be 0.5.
No. I know, and that's why kids get this one wrong. They're like, oh, well, the intersection here is not quite what they're looking for. And here's the issue, guys. They didn't tell us like the rest of the Venn diagram. You notice how they haven't discussed sophomores, juniors, seniors, like at all? So we can't just simply like subtract like we normally do. We have to think of it this way. 20% of the freshmen are athletes. So 20% of the 35% is what you guys have to do. Okay, that's a little trickier than normal. I think it's 7%. Now, my friends who were doing like this out of 100 athletes and 100 freshmen, 100 kids, you would do the same work. You would find 20% of 35 and go, oh, look at that. It's 5 kids. No, 7. Gosh, I said it backwards. So this number is what goes right here. That's really tricky. Trickier than normal. Okay. We're not looking at the whole sample space as part of the problem. So now that I do have this intersection piece, yeah, we need to do a little subtraction now. There you go. So this is going to be a 28%. You got that from 0.35 minus the 0.37. And then over here you got the 0.22. 0.29 minus 0.07. Yep, you can do the outside pieces. So there's 57% out here in no man's land. You can find that by adding these up and subtracting from 1. Yeah, they add up to 43 and then do the complement of it. Right? Or did I do that wrong? Did I not subtract from 1?
No, you added 0.28, 0.7.
Oh, that's 0.57?
Yeah, that's total.
Oh, see that?
43.
See, we're finding a whole nother set of problems on my key. Sorry, guys. Good catch. I'll fix that. The good news, though, is we still would have got the question right because the question has nothing to do with those others down in the corner. The question says, what is the probability that you will choose one student who is not a freshman and is an athlete? Okay. So this number over here, I don't have to worry about because it says and an athlete. So they have to live in the athlete circle. But of the athlete circle, I only want to include people who are not freshmen. So wouldn't that be like this piece right here? Okay. So what percent we're looking at there, guys? 22%.
Well, we have times the 0.29. I thought we had times.
No. So the 0.29 was the entirety of the athlete circle. So it's saying 29%. That's including all these pieces here. That's a good question. Now, those of you who just love a good formal probability notation, what you guys were trying to find here was the probability of not freshmen and athlete. So that would be what the notation would look like. That's not necessarily going to be a big part of your test, but I know some of you like to kind of resort back to formulas because that's a comfortable place for us. So I think that's one of the trickier questions on the test. So watch out for that one. All right. The next one, though, is not tricky, especially if you can come up with a pretty terrible sample space like I'm about to. So we roll 2 dice. What are the possible outcomes when you roll 2 6-sided dice like normal die? You could have a 1-1. You could have a 1-2. You could have a 1-3. Now, for me, I'm lazy, so I'm not going to sit here and write all of them out. I'm going to do one of these. But I could also have a 2-1, a 2-2, ... down to a 2-6, and then ... down here, all the way down to a 6-1, a 6-2, ... 6-6. There are very few instances in my life where I would literally write out all 36 outcomes. Only if I was really, really, truly having a problem with this question. So, it does say find the probability that the sum will be less than 5 given that you roll 2 even numbers. So you're trying to find the probability that your sum is less than 5 given that you roll 2 evens. So if you were to write all of the sample space out, every single one of them, what you would want to do is circle, highlight, box in somehow all of your conditional probability components. So 2 evens. What would be an example of me rolling 2 even numbers? 2, 2. What else? 2, 6. We missed somebody in here. 2, 4. Would that be 2 evens? Yeah. Okay, and you could keep going through that. So 2, 2, 2, 4, 2, 6. 4, 2. 4, 4. And 4, 6. And then 6, 2, 6, 4. And 6, 6. So to be honest, when I did this question, I didn't even bother to like really write out the sample space. I just wrote out what it looks like when I roll 2 even numbers. So I wrote out 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, so on and so on. So how many possibilities do we have here for our denominator? 9. So out of those 9 possibilities, how many of them provide a sum that is less than 5? Just the one, right? Just this guy right here. So only one of those 9 outcomes would satisfy this probability. There we go. So when you have a conditional probability based on a sample space, you have to realize that it's going to limit your sample space. Your denominator is no longer all 36 outcomes. It's limited to whatever the condition is. You could have relied on a formula here, guys. You could have said, all right, well, I'm going to find the probability of having a sum less than 5 and rolling 2 evens divided by the probability that I roll 2 evens. Well, guess what would happen, y'all? You'd end up with 1 over 9. The formula works all the time. You just have to decide if it's worth your effort to go through the formula or if a visual approach is different. For most people, a visual approach is different. Questions so far? All right. Now I'm happy because they've already given me the two-way table with totals, which I love. So this one should be nice for us. If you, yes. I'm going to be honest. I was really quite nice to you on this review. I pulled questions off your test and just tried to change them. That's where the infamous sock problem came from. 2 striped socks that you put back the first one for some reason. All right.
You're a very thoughtful person.
Well, thank you. Maybe I will put this video on the internet. I know. I didn't understand either. I don't know. Kids are weird, man. Okay, so we have a two-way table here, and it's dividing freshman, senior, and staff versus going, not going, and undecided. I don't know where they're going. I don't know if I care. They're going somewhere, or not, perhaps, or perhaps they're undecided whether they're going. I don't know. That's right. That fishing marathon. That's right. Okay, so find the probability that a randomly chosen person is going or is a member of the staff. Now, if you love formulas, what you're going to do is you're going to find the probability of going, or that they're on the staff, which means the formula says you take the probability that they're going plus the probability that they're on the staff, but you have to subtract the probability of the people who are going and they're on the staff. Because you'll notice if you bust out a highlighter or circle things, the people who are going intersect with the staff. So here's the people that are going. And then here's our staff. So if I'm using the formula, what I'm going to do is say, all right, there's 95 out of 202 people going. There's 62 out of 202 people who are on the staff. But then these 40 people were counted twice. So we're going to subtract off 40 over 202. Now, if you're super lazy like me, you're just going to crank this numerator in your calculator and then divide it by 202. Decimal answer works great for me, y'all. You should get a 0.579, I believe.
So my shadow is basically
Yeah, I mean, pretty much. Yeah, I didn't put anything extra on there that you're not going to see, that's for sure. Now, was there another way to get that number? Yes. We could have done that like pieced together thing. So like if someone counted all of the people who were going and they said, oh, well, there's 95 people going. And then they counted these extra two categories of staff members, they would have got the same answer. So without subtracting the overlap, there's other ways to get it. Just be careful that if you're using the formula, you use it all the way through. You subtract the overlap. All right. Same stuff, but now we have a condition, has the magic word given. So what's the probability that a person is a senior given that they are not going? Now here you got to focus on the given. So it says given that they're not going. So we're talking about just these people here. So what's going to be my denominator in this conditional probability? Yep, it's going to be out of those 85 people. So out of those 85 people, how many of them were seniors? 45. So probably want a decimal answer there. 0.529. Sure. So again, it's going to be a multiple choice question. Probability notation, while is very informative and helpful, if you feel like you don't need it, then don't bother using it. But this notation would have said this, right? Probability that someone is a senior. Whoops, not that. Given that they are not going. Now, if you just love formulas and you want to use the conditional formula for that, go ahead. But I really, truly feel like if there's a display of data, you're better off just using your common sense, if you want to think of it that way. The formula does help if you're stuck, but you don't always have to use it. All right, was that the whole review?
Yeah.
Excellent. Well, I can stop this video.